Welcome to Chapter 8 on parabolic problems. In Chapter 2, we modeled the temperature in a reactor. And if you remember, what we did is that we considered a domain omega with its boundary d omega. And we considered two variables, the time variable t, space variable x. And we considered the unknown that was the temperature theta. We had some data, the density of the fluid inside of the reactor, the velocity of the fluid going through the reactor, the source of heat, well, obviously it's a reactor, and then we had some parameters, C and kappa. Now, based on this, and I suggest you go back to Chapter 2 if you forgot, we derived the heat equation, which is right here. Or actually, what we did is we derived the heat equation when the fluid did not move, and that was that equation here, where the divergence term of rho c theta u is actually removed. So what you're left with is this equation here. So in other words, what we have is a temperature theta that changes over time, right, as the heat will spread throughout space, throughout the reactor. So that temperature will change over time at a given point. And of course, it will also depend on the point where you're looking at the temperature. So theta is a function of four variables, t, and the location x, which is x1, x2, x3. Or xyz if you prefer, then you can call the location x in this case. I mean, just a matter of notation. So in any case, theta is a function with four variables that returns a real number. And the equation that you get is this one. The heat equation really is time derivative of theta minus a coefficient alpha times the Laplace operator applied to theta equals f. Now, in the previous equation, I had the divergence of kappa del theta. And just for the sake of simplicity, I consider kappa to be constant with respect to, well, time, of course, but also space. And that what I get here is this equation right here, where alpha is the thermal diffusivity, which will depend on the different parameters that we talked about earlier. Okay, so that's my alpha. I have some directed boundary condition. That is the second equation right here, which is theta on the boundary is a prescribed temperature, theta p. And I have some initial condition, which means that when t is equal to 0, the temperature is known everywhere in the reactor. Possibly it is simply the temperature, the same temperature, is just, we didn't do anything, so everything is at the same temperature. That's a possibility. But at any rate, what we have is that the temperature is known at time t equals 0. So this is the equation that we have, and this is the equation that we will study in this chapter, or rather, these types of equations that we will study in this chapter. Now, the temperature is called theta. Just out of consistency with the notations that will come up, I will call the temperature U. So this can be a little confusing because U was the velocity of the fluid, which we consider actually to be equal to 0. So I'm just changing the notations here. U will be the temperature from now on, and I will call UP the temperature that is prescribed on the boundary of my domain. All right, so this is what we have in dimension 3, which obviously is the real problem of the reactor. Now, we can also consider the heat equation in dimension 1, either because it's a gross simplification of a problem, because there are some symmetries, or simply because we have a rod and we just consider this rod to, after simplifications and, symmetry and a lot of things, to basically, we consider that we have the heat equation, which is given by this problem here, du over dt minus alpha du over dx squared equals f, right? This is going to be the heat equation in dimension 1. And again, what we have is that the location at this point is going to be x. In other words, it's going to be a real number. So we have one dimension in space and obviously one dimension in time. So u will be a function that will take two variables, t and x. And again, we have, as we said, directed boundary conditions, and the initial conditions u0x equals phi of x. So this is what we have for a heat equation in dimension 1, which means that the function will be of dimension 2 because you have time and space. So when I say dimension 1, I mean dimension 1 in space, which of course when you add the time, then that becomes a dimension 2 altogether. All right, this PDE is parabolic, okay? And if you forgot why it's parabolic, again, go back to chapter 2 when we did classification of PDEs. This is parabolic, which means that what we did in chapter 4, 5, and 6 is not going to apply, right? Remember, when we had to have a elliptic PDE in order to apply the variational problem, the finite element method, the finite difference method. All we did, we really relied on the characteristic that it was actually an elliptic PDE. So we obviously are going to encounter some problems here, and these problems is exactly what we're going to discuss in this chapter, because we're going to see what we need to do to overcome these difficulties. All right. So we're going to have some questions. The first question is this PDE well posed? And possibly, what are the properties, the qualitative properties that we have with this PDE? That's going to be the first question. And of course, there is another question which which comes as well, which is, can I approximate the solutions? In other words, can I use the finite difference method? Can I use the finite element method? What can I do to approximate the solutions? And again, we did this for elliptic PDEs before, and what we're going to do in this chapter is to extend this to parabolic PDEs. Now, before we talk about this, I would like to point out something that I just said earlier. I talked about, I said time and space variable, and that I would like to say something about this. What I would like to say is that mathematically speaking, there is not such a thing as a time variable or a space variable. There are variables, but there is not such a thing as a time or space variable. Actually, it's not a mathematical concept. But we have variables that can model time, and we have variables that can model space. And what is going to happen is that when we observe a phenomenon that has reached an equilibrium, time no longer will play a role. And so, as you know, we will have what we call the steady state, which usually, or actually often, leads to an elliptic equation. Again, this is what we've studied in the previous chapters, and more specifically, chapters 4, 5, and 6. For instance, if you take the heat equation and you basically remove the time derivative of u, what you obtain eventually is the Poisson equation minus Laplace u equals f, right? So I wanted to point this out. There is not such a thing as a time or space variable, but for practical purposes, coming from modeling, we will actually have time and space. Actually, there is something else which is interesting, which is that even though we don't have a time and space variable, mathematically speaking, we will have some behaviors that will be actually drastically different with time and space based on the fact we have one derivative on time and, obviously second derivative in space. So actually, there are a few things to be said about this. We won't get into too much details here, but that's something that I wanted to point out. All right. So when time plays a role, usually we denote it t as time, And for the space variables, we usually use the variable x, and x1, x2 if you are in dimension 2, or x1, x2, x3 in dimension 3 as we did before. We can also use x, y, z, so these are standard notations. Of course, if you are in dimension 1 in space, it means the PDE will be of dimension 2 because of the time variable that you have to add to the mix. And same thing, if you're in dimension 2 in space, then the PDE is of dimension 3. And if you are in dimension 3 in space, then of course you are in dimension 4 for your PDE. Okay, at this point, many students are probably thinking, okay, there is obviously two things to do. The first thing to do is to work with the theoretical aspects. Does the solution exist? Is the solution unique? Do we have well-posedness, basically, as we said? And what are the properties that come with this equation? But there is also another question, as we mentioned, which is, how can I approximate the solutions? And many students are probably thinking, do I really need to work on this, or isn't it something that we already covered when we did the finite difference method? And let me explain. If you look at this equation, we could say, let's try to apply the finite difference method, right? I mean, the finite difference method is just a way to approximate the derivatives based on points of the grid. So all I would really what I would like to do is to say, okay, let's just try to do a finite difference method scheme on this equation. So I'm going to consider the time. I'm going to subdivide my time interval. I'm going to subdivide my space interval, and then I'm going to apply the finite difference method as I would have, two chapters ago. Can I do this? Well, let's try, right? Let's try doing it. Okay, so here is the equation that I have. So I took it in dimension 2, dimension 1 in space, which gives me a dimension 2 altogether. So here's my equation. And I have the boundary conditions, ut0 and ut1, that are equal to u0. And the initial condition, which is u0x, which is equal to phi. And just to simplify things, I will consider u0 to be equal to 0, and phi to be equal to 0. So what I'm left with is du over dt minus alpha du over dx squared, d second u over dx squared equals f, where f is a given function. And u is equal to 0 on the boundary and 0 with the initial condition. And by the way, the function f I will choose is just a function f that will be equal to 0 everywhere, but on the small segment where it will not be equal to 0, and it will be constant. So let's do things very simply here. All right, so based on the chapter on finite difference method, let's just consider a uniform mesh of 0, 1, and I will consider jx plus 2 nodes, including the 2 nodes at each ends. And let's mesh 0t with jt plus 2 nodes as well, which means that I will have 2 steps, one space step, which is hx, and one time step, which is ht. So here's what I have. Now, I'm going to approximate the value of the solution to this PDE with boundary conditions and initial condition. And I'm going to approximate this unknown u at the point I times ht and j times hx, right? So that will be a point of the grid. I have a grid, right? I've basically subdivided my time, subdivided my space. So what I'm going to look at is what I have. I mean, I want to approximate the solution at the point I, ht, j, hx. And I will denote this approximation by u, I, j, where I is a superscript and j is an index. Now, you remember when we did the ordinary differential equations in chapter 1, I told you I'm going to put the index actually as a superscript rather than a subscript, because at some point, thinking chapter 8, then I will want to have the time on top as a superscript and the space discretization on the bottom as a subscript. So that's why we did this. So you see Uij, I is a superscript. It really will be the discretization of time, the time interval, while j is a subscript, an index if you prefer the subscript, and that will denote the subdivision on the space interval. All right, so we already know Uij when I is equal to 0, right? Because that's the initial condition. And again, I means discretization of time. So when I is equal to 0, so when you start, that is your initial condition, and you know that it is U0x is equal to 0. So what I'm saying is U0x equals 0, therefore U0jhx is equal to 0. Therefore, Uij will be equal to 0 when I is equal to 0. All right. Now, we also know Uij if j is equal to 0, right? Because in this case, what you have is the boundary condition ut0 is equal to 0. So you have Uij equal to 0 in this case. And on the other end of the interval, then when j is equal to jx plus 1, then what you have is that Uij is going to be equal, well, I mean, Uij is going to be equal to 0 because obviously it's the boundary condition on the other end. So this is what you get. So this is what you know. I mean, this is the information you know. So you have Uij when j is equal to 0, j is equal to j plus 1, and for every single j when I is equal to 0. All right. Now let me denote fj, f evaluated at jhx. As you know, the second derivative of u with respect to x can be approximated by this quotient. And if you forgot why, then you want to go back to chapter 6, where we explain why this is so. And the same way, the time derivative, first derivative of u is going to be given by this. And here I choose a forward difference quotient. I could have chosen something else, but I choose a forward difference quotient. Actually, there is a reason why I'm choosing this. Okay, so this is the approximation of the second derivative of u with respect to x, the first derivative of u with respect to t, and not only the approximation, but actually the exact value of f at jhx. So if I consider the point tx, which is iht jhx, then I can really compute well, fj obviously, but the second derivative of u with respect to x and the first derivative of u with respect to t based on these formulas evaluated on point of the grid. And here is what I get. Okay? Now, when I consider the equation that I'm interested in, which is du over dt minus alpha d second u over dx squared equals f, then I'm going to substitute these expressions in that equation. So what I'll get is this. I'll get, well, basically, let me replace. I'll get this here. Well, obviously the right-hand side will be replaced by fj, and I'm going to replace the second derivative here by this expression up there, and I'm going to replace the time derivative by this expression over here. So in the end, what I obtain is this. Let me actually put that up over here. What I obtain is this. Let me rewrite this way. I have uji plus 1 minus uji divided by ht, which is equal to this right-hand side. So let me actually multiply, get my ht over there. And let me actually just write this way. Okay, so what I have is uj I plus 1, which is equal to a bunch of terms where I basically have terms with ui. I mean, I have ui, uij plus 1, uij minus 1. But what I'm saying here is that on the right-hand side, nothing that appears on the right-hand side is at a time which is not, the only time that appears here is I, the time discretization, of course. While on the left-hand side, it's I plus 1. So really, if I know what happens when I is equal to 0, then I can probably compute what happens for I equals 1, and then what happens for I equals 2, and so on and so forth, right? I mean, just as a reminder, I know that uij is equal to 0 when I is equal to 0, and also on the boundaries, which means that when j is equal to 0 or j is equal to jx plus 1. Okay, so let's actually implement this in Python, right? I mean, obviously, we know how to compute uij, provided that we start with we actually start with a bunch of zeros, right? I mean, we know that we're going to start with uij when I is equal to 0 is going to be only zeros, and then, as I said, you can basically compute u1 and compute u2. So basically what you need to do is to do a loop. That's basically what you need to do. So we'll be able to do this in Python. So let's do this in Python. Let's actually program this together. So here is the program that we're going to use. So first, we're going to import a few libraries. We're going to use to import NumPy. Obviously, we're going to do some computations here, and we're going to also do some graphs. So we're going to import matplotlib and also some animation parts of matplotlib. So that's why we're doing these 3 imports. Then we're going to give a value for the coefficient alpha, and I will just consider 1.0, I mean 1, which at this point, we're going to define our space domain. So our interval is 0, 1. I will call this x min and x max, and I will choose 0 and 1 for this. And now what I'm going to do is a discretization of my interval, right? So I'm going to choose jx. For instance, I can choose jx equals 10. And of course, I'm going to define hx as x max minus x min, which is going to be 1, divided by jx plus 1. Okay, that's for the space domain. Now, for the time domain, I'm going to start the experiment at 0, and I'm going to see what happens when time is equal to 3. So here's my time domain. And I can choose a discretization here. For instance, I can choose 3000 or 300. So let's actually compute here. I mean, actually put a JT here that will be the discretization of the time. And of course, HT that goes with it. You're probably wondering why I'm going to print this value, which is alpha times ht divided by hx squared. I'm just putting it here because that is a coefficient that will be of interest. So I just wanted to print it. As a matter, this will be called the CFL, and we'll talk about it later. But I'm just writing this right now. It doesn't make sense, but I'm just writing this value. Okay, now what are we going to do? First, we're going to initialize our vector u with 0. So I'm going to first start with u is empty, and then I'm going to append to it basically to start with zeros. How many zeros am I going to have? Well, all the zeros inside of my domain. I'm not going to consider what happens on both ends because as you know, it's a directly boundary condition. I already know the values at both ends. So all I'm going to be interested in is what happens when j is equal to 1 to j equals jx. And therefore, I'm going to start with my jx zeros. That will be the first part of the vector. When I is equal to 0, then obviously u is equal to 0. I mean, all ui's are equal to 0. All right, now I'm going to discretize the source f, and as I said, it's going to be equal to 0 everywhere, but in between 0.4 and 0.6, it will have the value 50. Okay, so what I'm doing here with this with these instructions is basically building this this vector f, or fj if you prefer, that again is completely independent of time. It just depends on space. It will emit the same heat throughout the experiment. And here is the discretization, so it was just a simple way to write it. Of course, I could have done a loop, I could have done many things. That's a very simple way to write it. So basically zeros, then 50 times 1, and then zeros on my interval that has been subdivided accordingly. Okay, so we have our u at I equals 0, and we have our f, and we have basically an equation that relates ui with ui plus 1, right? So let's actually implement now this going from ui to ui plus 1. Well, and obviously this is going to be, we're going to do a loop over this, okay? So that's why we have a 4i in range jt. That is basically saying, once I know ui, I can compute ui plus 1 for all possible j's. So that's why I have this first loop in UI. I'm gonna build this UI, and so how am I going to do this? Well, 3 situations can happen. Let me start with the last one, with this one here, with the else, which is I'm not in the boundaries. If I'm not in the boundaries, what I'm saying is that I know how to compute uij. This is the equation that we saw earlier, right? We had uij plus 1 equals something. Well, that's exactly what I have here. I'm saying you happened what? Well, I'm happening this right-hand side. And what I suggest you do at this point is you stop the video, go back to the equation, and just make sure you understand how what's here in Python corresponds to the formula. It's important you do this so you really, understand what we're doing. So at this point, I suggest you stop the video, just rewind a little bit and go back to understand why what we have in the else here, in the else statement. So now you're back, and we have what happens if j is equal to 0 and if j is equal to jx plus 1. Well, this is what happens at the boundary. So what do we have at the boundary? Well, we know the value of u on the boundary, right? But if you look at what we have for the second derivative approximation, then we're going to have a term which is going to be equal to 0. So basically what we do is we take whatever was in the else statement, but we're going to remove the part that is simply 0 and just not put it there because it's 0. Right? So this is, in the end, what we obtain. We basically separate what's on the boundary from what's inside, and we simply implement the equation that we explained, that we saw earlier. So this is what we have. So we compute ui, and then we have u upon ui, which means that basically we're building u. We're basically adding this new layer, and so we're doing u0 was initially, we initialize u0, and then we do u1, u2, all the way to basically all the way, so we can have an approximation of u. At this point, we're going to include a few statements that will allow us to plot the solution. So, well, I would not worry too much about these expressions because it's really Python comments that will allow me to basically what's going. So what is going on? Okay, so let's actually run our program. So let me run the program, and here is what I get. I get this simulation. So as you can see, I start with a temperature that was 0, I mean, that's my initial condition. And again, we're hitting only on a part of the domain here, which is the center between 0.4 and 0.6. And as I keep hitting, what happens? Well, the temperature, well, in the entire domain actually increases. And it actually gets this profile here. And again, remember, we maintain the temperature at both ends. So the temperature at both ends is maintained. It's heated in the center. And so the temperature does this. And eventually, it looks like it doesn't really move anymore. I mean, well, it does move, but we can't see it moving because at this point, it really kind of reached its steady state, right? And by the way, if now that you master elliptic equations very well, you could actually try to see if you, I mean, to basically compute the solution for the steady state equation, which means to basically remove the time derivative. So it's something you know how to do based on chapter 4, 5, and 6. And you could see that the steady state is the solution, which is now actually on the screen. It doesn't move anymore. That's the steady state. We reach the equilibrium. Okay, so that's what we get for the time, for the discretization of a parabolic equation. So at this point, the people who are thinking, okay, we don't really need to spend too much time understanding what is going on with finite difference method for parabolic equations seems to have it right? I mean, in a sense, all we did was to apply the finite difference method that we discussed in chapter 6, and it worked. Okay, so it looks like, even though we did not prove it worked, it seems like it's kind of working. So okay. All right, so now let's actually change a few parameters here, and I'm going to increase my my discretization in space, right? I mean, I want to do better. I mean, you know, what I did before is okay, but I want to actually increase the quality of my simulation. So what I will do is to get a finer step with respect to space. So let me do this. And so I'm changing Jx here, as you can see, increasing it. So Hx is getting smaller. Therefore, I expect to have a way better simulation. So let's run the simulation again. Oops. Doesn't seem to work that well. What happened? Well, what happened is it seems that it doesn't work anymore. It doesn't work anymore. I mean, and this is completely unexpected. I mean, I was expecting the simulation to be better, right? Because again, when you increase the number of nodes, when you decrease the step, then you should have a better simulation. But somehow, something happened that we did not understand that actually made the whole thing go astray. So people were thinking just a few seconds ago, okay, we got this covered. Finite difference method actually allows us to do the simulation, and we're actually, you know, pretty happy about what we had before. It seems that there are still a few things we do not understand. And as a matter of fact, what we don't understand is that it seems, and you can do several experiments, and you can see that somehow, when the coefficient alpha ht over hx squared is too big, we run into a problem. So somehow that's something we don't understand why, but that at this point we will understand why by the end of the chapter. But obviously this is a problem. Okay, so while the finite difference method seems to be pretty promising, because it seems, again, I mean, we got some results earlier, it also seems that some theoretical works need to be done. And we need to understand that somehow there is a relationship between ht, hx, and alpha that will give me the convergence, or will actually prevent the convergence from happening. So there is something we need to understand. It's not clear at this point why that is so, and that obviously will be part of what we're going to do in this chapter. All right, so here's what we're going to do in this chapter. First, we're going to discuss well-posedness of parabolic PDEs. We have not done so, so let's do it. And to do that, we're going to first define some functional spaces, and then we're going to solve the heat equation. That will be section 1, 2 videos. Then we're going to discuss the qualitative properties of the heat equation. We're going to discuss regularity, we're going to discuss asymptotic behavior, and we're going to discuss the maximum principle that we already talked about earlier in previous chapters. So that will be 3 videos in section 2, qualitative properties. And then, well, obviously there is a lot of expectations here. That will be section 3, numerical approximation of the solutions. Well, obviously there is something fishy. So we're going to need to understand what is going on. There will be 3 videos in section 3. The first one will be what is called the semi-discretization using the finite difference method. The second video will be a semi-discretization but using a finite element method. And the last video, 3.3, will be the time and space discretization using, to basically do a numerical approximation of my solutions.